Okay, so I'm not sure how many people would join today because we are not going to have any attendance. But I guess I can wait for maybe one more minute. We start at 10:04. Okay. Okay, so how many people? 20 is fine. I was not expecting more than 20 anyhow. So basically this lecture and the next two lectures, we won't have a lecture on Monday, by the way. I'm not free. If you guys want, we have another lecture to compensate for it, but it's up to us, right? I mean, it's basically just a revision lecture. So if you guys feel that we need one revision lecture, I'm open to taking it at any other time, right? But at that time, I won't be available. So it's up to you guys. If you feel that uh, in three lectures we are not able to revise properly, then we can also find out a slot and uh, do it in its, let us say, an extra class. But we are going to have today's lecture and then next Tuesday and next Wednesday. And again, 6 p.m. this Sunday, there will be a lecture by Avanish, 1 hour lecture, and somewhere in the afternoon, um, we'll have the makeup exam for those who are interested in. In fact, let me just check how many people have. I think a lot of people have already opted in to give it like a practice test. So which is good. I mean, I'm quite happy that you guys are willing to take that as a as a practice. So that's really good. I was not expecting so many people to actually uh, to take up this particular exam, but it's nice. How many responses do I have? Very good, 53 responses. So it's nice that so many people want to take up the test for practice. So that practice test will be somewhere in the on Sunday afternoon, and 6 p.m. on Sunday we'll have Avnish's lecture. I'll send an email also. Okay. So any particular way you guys would like to revise, or shall I start from, let us say, the first, and I'll just keep on moving through slides. If you feel there is something that you would like to discuss, we can stop and discuss. This is what I had in my mind. But if you guys want it to be in some other fashion, we can do it as well. So I'm just assuming that it will be better if we just go about it, one by one. Okay, so let me start. First way, sorry. What was the first way?
So I think just was saying that we will go through the lecture, and if we have any problem, then we
That
will
I'll
ask.
just I'll just zip through each lecture, and if you have any questions, you can ask. Okay. Okay, so let me just go in full screen mode.
Sir, I think we have to go after the syllabus of mid-sem, like before mid-sem.
Actually, we did not revise anything at the time of midsem, so I
Okay,
thought,
sir.
right? So I thought we'll just
Okay,
uh,
sir.
right. So basically, this is from where it all started. Okay, so we said that what are computing devices? We talked about calculators, and we said that how exactly is a particular laptop, let us say, or a smartphone different from a simple calculator. So then we realized that in order to do some addition, you need, so these are some of the devices that you guys have already seen, things like a abacus. So we talked about what is a number system, that you essentially only learn about adding, some simple addition things that you remember, right? So what is 4 plus 5? You only remember that. Or what is 9 plus 3? You remember that. And then with the help of certain rules, you are able to do addition on a larger number of digits as well. We also said that these are the numbers that we have studied till now are all in base 10, but in computers we basically talk about base 2. There were so many things about this, right? That why exactly base 2? So one of the answers is that this is because of transistors. Transistors are an electronic component. I'm pretty sure by now you guys know what is a transistor. So it can either be on, or it can either be off, and this was representing the two states. We had some talks about quantum computers and stuff, but yeah, I mean, as of now we are a bit away from quantum computers. So this is what we have, right? We have computers with base 2, and we talked about what is the whole concept of Boolean algebra and switching theory. We said that Boolean algebra is basically a kind of algebra that happens over base 2. So the only possible values that a particular variable can take, 0 or 1. And we said that the AND function will give you the output as 1. If all the inputs are 1, the OR function will give you the output 0 if all the inputs are 0, and the NOT function will simply flip whatever was the value of a variable. If it was 0, it will become 1, and vice versa. Then we talked about the whole concept of. By the way, if you guys have a question, you have to unmute and stop me, because I'm not looking at the chats. So yeah, so basically we said that there is something known as a central processing unit of a computer, and the heart of the central processing unit is something known as the arithmetic logic unit, or ALU. Performs all the arithmetic operations as well as those logic operations that we just saw. And then there's another unit within ALU, within CPU, called the CU, or the control unit. This control unit is essentially a unit which controls exactly what instruction is going to be executed at what point of time on the system. And we also saw that there is something known as registers. A proper term is CPU registers, and these are essentially some storage devices, storage places where you can store some data, some zeros or ones, right? So the ALU, CU, and the registers, they constitute the CPU, the central processing unit of your computer, and that is the brain of your computer. And then we discussed that there is something called as von Neumann architecture. The von Neumann architecture is basically just whatever we just saw, the CPU plus some inputs and outputs added to it, like this. And you also need a memory where you are going to store some instructions, and then your CPU is going to fetch instructions from this memory and execute them. And then once the execution finishes, you store the results back in the memory. Okay, so this von Neumann architecture was basically the predecessor of what we call as a stored computers. And stored program computers are essentially what I just told you, that you basically, whatever instructions you want to execute over a computer, you store it inside a memory unit. And then there is a mechanism with the help of which you can store these instructions in the memory and then take the output of the computation. And this was known as the stored program computer. Okay, any queries in this? Shall we move to the next lecture? Okay, so this is how we started. And then the next lecture was basically giving you an idea of the operating systems. And so this is how we all started. What is happening? Why is it not? Okay, so so this is what we said, that basically a main memory, or the so-called RAM, okay, the common name for main memory is RAM, is the place where operating system puts all the instructions for the CPU to execute, and any data that is also required for the computation, that is also stored in the same memory, right? So the same memory, and I think I have still forgotten to change this. I remember there are only 15 boxes here, but there should be 16, as or no. So basically the idea is that this main memory gets these addresses. These are addresses of these cells. Okay, cells are basically one unit of storage where you store something or you retrieve something. So I've just written these addresses, and these are the addresses in decimal. So basically it is this main memory where the instructions are stored for a CPU to execute, as well as the data is stored. So um, so basically this is a simple example of how a probable program looks like in let us say assembly language. So it is not really assembly language. I have just created my own instructions here, but it is similar to something like this. So basically you say that there is some data at this location, right, 0110, and you basically say please load it in the AC or the accumulator register. Then you say that there is some other data at this location, please load it in R1, the first general purpose register. Then you say add R1 to AC, and then finally store the final result at some other location, right? Now we also said that AC is basically a special type of register. Okay, we said that AC is the accumulator register. This register is used by the CPU to actually store intermediate results of your computations. So usually we do something like this: we add R1 to AC rather than AC to R1, right? I mean, this is generally what we do. It is not necessary, but usually we use the accumulator register as the main register, the register where usually the computation results are stored. And at the same time, the CPU also has access to a number of general purpose registers, which are usually named like R1, R2, so on and so forth. And there is one more register called the PC, the program counter. The work of program counter, it actually it never stores a data item. Program counter always stores an address, and this is the address of the next instruction that my CPU should execute. So these are the things that you guys already know, I guess. um, I think this I have talked about. Okay, so this was just the example, and this we just went through this whole example. At each step what happens, so how exactly all these things are executed. Okay, so then we also discussed that in assembly language programming, uh, you have something. So you have to store your instructions in the memory, and this is basically some of the things that you need to understand. Again, the details of this you will study in computer organization, but basically, whenever you type a particular instruction, there are usually three parts in that instruction. So one is essentially the operation code. So here the operation code is, I mean, the operation you're trying to do is load data. So that is the operation. So you need to have some code for it. Then you also have an address. Address is essentially a place somewhere in the memory from where you are going to bring your data. And then there might be a register where you are probably trying to load it. So this is I mean, it is not fixed that this is exactly how your instruction looks like, but usually you have three components like these, right? There is a component for the operation that you want to perform. There is a component for some kind of address in the memory, and there might be another component like a register. So so we said that in order to represent this in memory, we use some bit patterns like this, and I say that this is completely on my own convention. That how am I going to interpret this? So in this example, I say that, let us say I have two bits. I have reserved the first two bits to represent a particular operation. So now I can have at max four operations on this computer, right? 00011011, which might mean 00 is load, 11 is something else, let us store, 10 is add, something like this. Similarly, I'm using two bits for representing a particular register. So I say that I can have at max again I can have at max four registers in my system, including the accumulator. So R1 and R2 could be given the codes 0, 1, and 1, 0, and then this 4 bits I'm going to reserve for the address of a particular location within the memory. So this usually is decided by the size of your memory. Okay, so this is what it looks like, and this is in the case where the word size is one, as in the you are going to store the whole instruction in just 8 bits. It could be that the word size is more than one, like two or more. So in that case, you get more space, so you get more number of bits to represent an instruction, and there can be more operations, there can be more registers, and a bigger memory can actually be addressed. So this was the overall idea. We also said that a typical input device is keyboard, and the operating system somehow knows how to deal with this input device, and these input devices are connected to the CPU by something known as buses. These are just wires, a set of 8 wires or 16 wires, something like that, and they basically transfer data from one point to another point. So the operating system contains a set of assembly language programs. Now you know what those programs are. They are known as device drivers, and the same is true for the output devices like printers or a laptop screen. The operating system knows exactly how to do this. So basically, the operating system has some of these these tasks that you are basically expecting it to manage the input devices, manage the output devices, manage your main memory as well, and then coordinate with the control unit to get some computation done. So this is why, you know, operating system makes your whole life very easy. Any queries on this, or shall we move ahead? Okay, so let's move ahead. Oh, sorry. Where is that? Just a minute, guys. Virtual machines. Okay, so then we also discussed the concept of a virtual machine. And in fact, you guys have spent enough time over a virtual box as well. So we said that what basically virtual machines are is that they somehow provide you the facility to run another operating system over a base operating system, right? So these are basically OS on top of OSs. So the software, the software layer that allows you to do that is known as hypervisor, and hypervisor are essentially programs that can emulate hardware. That is the property of a hypervisor, and over a particular hypervisor, you can create another machine, a virtual machine, and then install your own emulated operating system. So I think you guys are already aware of this now, that basically uh, this is what a particular this is the scenario of a particular virtual machine, that there is some hardware, you install a base operating system, and then there is a hypervisor, and then there are virtual machines, one or more virtual machines. Now you guys already know that whenever you switch on a particular virtual machine, your RAM and CPU resources are only allocated when it is on, and as soon as you switch it off, the resources are cleared. But the space, right, the hard drive space that a particular virtual machine takes up, that remains. Okay, so even if it is switched off, it is still occupy that much space on your disk. And then you can, as I said, you can install your own favorite operating systems over that. So I think most of you have at least tried installing, let us say, Ubuntu over a Windows operating system, right? So so this, I think you guys already know VirtualBox and stuff. Okay, any queries, or shall I close it? Okay. So is this a better way, or shall we like do it in some other way? I mean, I'm not sure how to how to do revision. I'm just you know, browsing through the slides. If you guys feel that there is a better way to do this, please do tell me. Okay, where is it? 1.1. Huh, here. Hmm. Okay, so basically, this particular lecture, from this particular lecture, we started introduction to Linux. Okay, and
So, so
yeah,
your screen is not shared.
Oh, okay. Sorry.
Means like it's written you are starting to share content and a black screen.
Okay, let me reshare it. It visible now?
Yes, sir.
Okay. So this was basically the from here onwards we started our introduction to Linux, and we had already seen what an operating system was. So now from here onwards we started looking at how a particular system boots up, right? So basically there is something known as a ROM, a read-only memory. Okay. Now again, we've had a lot of discussions over it. The technology has actually advanced quite significantly. So these days, uh, these programs are actually stored in a kind of flash drive, I would say. Okay, so they are no longer ROMs. But yeah, for now, when you're just trying to understand the process, just consider this, that this is a read-only memory, which can only be read and not written to. It is not accurate for the modern computers, but yeah, the initial computers, it was pretty much like this. So what happens was there used to be a program that was stored on this ROM, and this was the first program that was executed as soon as you switch on your machine. And this particular program was also known as BIOS, or Basic Input Output System, and it used to perform a test called the power on self test, or post. The idea of post was to just figure out if everything in the system is as per expectations. So for example, do you have a RAM or not? Do you have a keyboard or not? So basic devices which are probably required for the operating system to work well. So now this is a more detailed diagram of the computer. You can see that the whole CPU, ROM, and memory things are residing over something known as a motherboard. So this is how your computer looks like if you open up a typical PC, for example. I'm not sure how popular is PC these days, but yeah, it used to be there. And all these components are actually soldered on a motherboard. Okay, so it's not like they are not really, except for the memory. Memory can actually be plugged in and plugged out, but everything else was basically soldered on a motherboard. And now for there is something known as a boot sector. So what exactly is boot sector? Again, it has changed in the modern days. So nowadays you can actually make any location within your drive as the boot sector, with this, I forgot the UEFI interfaces, right? That it is possible. But yeah, again, if we just want to understand how the initial computers work. So the boot sector used to be the first sector of a particular device, and it used to contain a particular program. In fact, I'm not sure how many of you have seen something like this, but it's very common. If you have a rather old PC or a slightly old laptop, you can see something like this there. And so what used to happen was that you can store certain preferences, like I want to boot from this particular device. It could be your hard drive, it could be a CD drive, and in the older days we used to have CD drives. It could be a pen drive. Basically, you had some kind of a boot order sequence that um the booting process, whenever it used to start, the first place will be this device, the second place will be this device, and what it will look for is basically the boot sector. Okay, and this boot sector, as I said, used to be the first sector of that particular device. Now, of course, things have changed, but for all intents and purposes, you can basically assume that in most cases it is the first sector of a particular storage device. And this particular sector used to have a small initial program. Okay, and that initial program had the ability to either load the whole operating system, or load another program that can load your operating system, and this was known as the bootloader. Okay, and yeah, so what else is here? Yeah, so basically there is something known as the kernel. Kernel is essentially the core of a particular operating system in the Linux. In the Linux ecosystem, kernels are actually created by a very elite, a small group of people. You can actually contribute to it, but whether your contribution is accepted or not, it is decided by a small set of people, and they basically say in the next version of kernel these all things will be included. But one of the major uh, uh, one of the major component of the kernel are the device drivers, where basically they are basically assembly language programs which can interact with uh, different types of hardware, right? So now this is another picture here, that basically, within your operating system, probably the lower part of the operating system can be considered to be consisting of the Linux kernel. And we talked about the different types of Linux flavors. We said that there is something known as a shell. So a shell is essentially a kind of command line interface to access your kernel. And we said that shells are not a part of the kernel. They are just, as I said, right, a way to interact with your kernel. However, when you download a kernel, usually you will have shell as a part of it, because there is actually no other way to interact with the kernel if you do not have a shell. So graphical user interfaces, the ones that we usually use, they, their collections are also known as desktop environments. Common examples are Genome, KDE, Unity, and they also, work over the kernel. Okay, so the kernel is the common part of the operating system, and shell, you can either have a shell based interface or a graphical user interface to interact with it, or a combination of both. Something like this. These applications and programs could be, these are all terminal based applications, and then there can be a desktop environment over it. So Ubuntu is a flavor of the Linux operating system, and we call these as distributions. Some other ones are Linux and Fedora. Um, so basically, a particular Linux distribution is just a collection of applications, okay, that run over the Linux kernel. So the different set of applications give you different distributions, and there are at least two versions of almost all the distributions. There is a server version and there is a desktop version. The desktop version contains utilities for UI, and the server versions are basically a shell only. The default desktop environment that is there in Ubuntu is Unity. I actually use LXDE, so that is why the version is also called as Lubuntu. So you can see that there are so many variants that are there in the Linux ecosystem. And then so this is just a simple example. I think we have had a video of how this can be done. So now file system. So basically, whatever files are stored on your machine, they have to be stored with some kind of management, and this management thing is the file system. And you have different types of file systems available: FAT32, NTFS. In the Linux domain, you usually use these ext3 and ext4. Now, different operating systems may actually support only some of these file systems. It's not necessary that each operating system supports each file system. But yeah, modern Linux distributions can usually read or write FAT32, and TFS as well. But I don't think so the Windows world is still supporting ext3 or ext4 or not. I'm not sure. I mean, it could be, or it, but at least till Windows 7, I would say, ext3 and ext4 was not supported. Um, yeah, so there is also something known as LVM, the Logical Volume Manager. I don't want really you guys to go too much into detail of this, but basically, this is another way of managing your actual disks that you attach to a system. So an LVM creates a kind of a layer over your physical devices, so that you can actually pool them up and create one large partition. The common term is partition. So this I think I will skip. Okay. Any queries on this? Okay. Yeah, I'm going at a very fast rate because I think this is just revision. But if you guys want, we can stop anytime. Point two. So basically the second part of this lecture was more about kernel. So this was an analogy that the kernel is basically, if you consider your computer as a restaurant, and the applications that are running are a customer, kernel is basically the employee that serves the customer, and the kitchen is the hardware. So you tell whatever you want to the kernel actually goes inside the kitchen. That is, it talks to the hardware, and it serves you whatever you want. And the way to do that, this whole communication takes place using what are known as system calls. So you make a system call, it is a request to the kernel for using a particular service that the operating system provides. The kernel does that, whatever you want, and then returns the results to you. um, so basically the set of system calls are actually fixed for a particular platform. So let us say on Linux, each kernel will have a set of fixed system calls. You can have a look at what those system calls are. So basically, whenever you want to do something on your computer, what you do is you ask the you know you make your programs, or you make your requests in such a way that they can be composed out of one or more system calls that are provided by the kernel, and then with the help of that you actually build your own applications. So basically, in some ways, system calls are like the alphabet, and then you can create your own words using different elements of this alphabet. Yeah, so typical system calls are to take input, produce output, open a file, start network connection, so on and so forth. So now, as I said, so basically a shell is a kind of command line interface to system calls. So essentially what you do is that, I don't think this is relevant. Yeah, so bash is a kind of shell that allows you to run some terminal, run some programs, right? These programs are essentially, and this is a term that I had used. It's that a bash is a kind of meta application. It is an application that allows you to run other command line applications, right? And so a typical bash consists of a collection of programs or commands. Each command in itself is an application. It in the background, what it is doing is it is basically invoking these system calls, and it is providing you some particular service. um, so this is how you do it. I think all these things you guys already know. So we had a look at the cat command. It is used to um, you know put data inside a particular file, or it can also be used to show the content of a file. This was the example. Okay, so here I'm putting some data inside a file using the redirection. So this will actually put whatever you type here inside the file, and then cat space the name of the file will print its content. And we talked about man pages. So man pages are essentially manual pages. You type man space anything, and then you can see the manual for that particular command, like this. This is the ls command. It shows you the listings. Okay, this is the cd command, this with the help of which you can go inside a particular directory. The dot dot essentially means you go back one step, and just cd, typing just cd will take you to the home directory. Pwd command tells you the present working directory. The mkdir command makes a particular directory, right? You create a new directory. The grep command, this is the command that I think you guys probably have used a lot. So the grep command looks for certain text within a set of files. This is the syntax. I think we have discussed it in at some great length. That the idea is that the difference between grep and find is that grep is used to uh, look for a particular text within a file, and find itself is used to find files within a set, let us say a set of directories. There is some specific syntax. I think I'm going to bypass that part. The clear command simply clears your terminal window. I think we have used it in one program, the if I'm not wrong, in the array program or the linked list program, we are using this clear system call in uh, the code itself. So this is a very simple and yet a very powerful command. And then there are editors on bash. Okay, the most popular one is probably vi. I won't call it most popular, but probably the the most ancient and most frequently talked about. um, that is the vim. There are others like nano. I mean, I'm pretty sure you guys already have some preferences. The sudo command is essentially a command that is used to get super user privileges. So whenever you type sudo and then you essentially type something else, whatever is executed, it's executed as a super user. In fact, sudo stands for super user do. Oh yeah, so basically then we just used this command sudo apt install build essential. It had the GCC, the C compiler that we used for our our whole course. Any questions here? Okay, so we are moving very fast. We're now in week 2. Okay, so from here we actually decided to look at algorithms and procedures. We took the example of quadratic equation. We said that in order to solve a quadratic equation in the standard form, which looks something like this: ax square plus bx plus c equals 0. The step involves finding the discriminant d equals b square minus 4ac, and then there are some conditions like this, and then this is how you find the root. So this is what I said, that if you want to explain it to someone in a systematic fashion, this is exactly how you explain it. And we said that whatever you just wrote is actually an algorithm. So an algorithm is essentially a sequence of just well-defined steps towards solving a problem. The issue, of course, with algorithms is that there's really no defined level of details. Okay, so it could be very abstract or it could be very detailed. Okay, but essentially it's all an algorithm, and algorithms are not intelligible to computers. Okay, it's basically for us, for human beings, to explain the process from one purpose, to pass the process from one person to another. In order to actually make a computer understand it, you need a compiler and a program. Okay, so basically this is what we said, that in order to write an algorithm, we have to come up with the idea of what the inputs are. And in this particular example, for example, we know that in order to solve a particular quadratic equation in the standard form, the three inputs I need are a, b, and c. If I know these three coefficients, I can calculate my discriminant, and I can check, I can find the roots. So basically in this particular case, the inputs are the three coefficients. Similarly, the outputs here are at max 2. You can have at max 2 roots for a particular quadratic equation. So this was a particular uh, image that was more interesting for us. And then we said, what is pseudocode? So we said that Algorithms could be written in plain English, which many a times uh, are far away from a program. A pseudocode is more of a constrained language. It is written in a constrained language. This constrained language is often uh, often closely resembles to the programming language which we are going to use in order to write a program. And this is, for example, an example. This is the algorithm, what we wrote in the algorithm, and this is in the pseudocode part. Again, this pseudocode too is not executable. It's probably just a midway between a program and an algorithm. Okay, so this is the pseudocode for solving a quadratic equation. A procedure is essentially a collection of instructions. Now you can probably understand this, that procedure is the equivalent of a function at the pseudocode and algorithm level. And so here you can see that what I have done is I have created a procedure for calculating discriminant, and I'm passing the three inputs to it, and then I'm expecting a returned value in which will be stored in D, and then this is how my procedure discriminant calculator looks like. Um, yeah, so this is the part. Any questions? Okay. So then we went ahead and looked at what are variables, constants, library functions. We said that variables in particular pseudocodes are things like A, B, and C, right? In the uh, in that particular example, we said that constants are essentially this squared, this 2, this minus 15. They are all constants. They are not going to change if you are trying to solve a particular. Sorry, these are not really constants. I mean, if you are trying to solve a particular equation, then these are constants, but otherwise they'll become a variable. So this was the kind of confusion that I wanted to remove, that in what cases there is a particular a particular element of your program is a constant and a particular element becomes a variable. So this was, I think, in the programming terms, we wrote two different programs. One program was just solving this particular equation, and then the second program was solving any quadratic equation. So when we wanted to solve any quadratic equation, um, this 1, 2, and minus 15, they were no longer the constants. We were supposed to treat them as A, B, and C, and A, B, and C became the variables. But you still have some constants. For example, here the square, the 2 is a constant, 4 is a constant. So this was the overall idea. uh, Covered. Okay, so this was the pseudocode. We just identified these are the variables and these are the constants. Then we talked about library functions. We know that library functions are basically functions which are written by someone else, and we are going to use them. Uh, so we saw that one example of the first library function that we used was sqrt, and that sqrt was in the math.lib. Any questions on this? Okay. Then from here onwards, we actually started a proper introduction to C. We started writing some code. Um, so I think the first code we wrote was for this quadratic equation itself. So we started out like this. We declared some variables a, b, and c. Then we did some computation like this: b square minus 4ac. We used a library function called sqrt to calculate the square root, and then we finally just calculated the roots like this. Okay, so I think this part is already clear to most of you, but still, so this is the part where we are declaring variables. A, B, and C are types of integers, and we are giving them values 1, 2, and minus 15. So whenever we said that whenever we create a variable, essentially some space inside the main memory is reserved. It's because it is an integer, there is an associated amount of memory, so that is mostly 4 bytes. So 4 bytes in the memory are reserved, and we assign it some value, and then that value is in this case 1. And then this is a library function. Whatever you pass this library function a particular value as input, and there is some computation here, and then the output gets stored back in the root d variable. This math.h is essentially a header file. A header file is essentially a collection of some library functions. Not really the collection as in the code, but basically a kind of declaration saying that this is a method that the user might use. The actual collection, the actual code of that particular function is linked at the time of building your executable. This is something that we just discussed in the previous week. How exactly does it happen? And then there is also, by the way, a digression lecture. If you guys want, you can have a look at it. Go ahead.
So please explain dot H. Yes, sir.
Yeah, so .h essentially is like this. A header file is basically a place where you collect a lot of declarations. Usually, okay, it's not necessary. You can also provide the definitions there itself. But the common practice is that we create a header file where a number of declarations are there, right? So it simply says there is a method like sqrt, which takes a double as an input and which returns a double as an output. But exactly how you are going to calculate sqrt, that is not there. So what we do is the actual code of sqrt is written in some .c file. You compile the .c file to create a file containing some object code. Usually the extension for these files is .o, and then you supply the binary code of the library. Okay, and this is why we need that minus lm switch, right? If you want to use sqrt, you have to use the minus lm switch. Why? Because even though math.h will give you the declaration, so the compiler will say, okay, fine, you are going to use a function called sqrt, so that is fine. But at the time your linker produces an executable, at that time you also need the code associated with sqrt, and that code is not given in the form of a c file. It is given in the form of some binary object code, usually in the form of an o file or a .so file. So stands for shared object. So usually all your libraries, their binary code is provided in terms of a .so file, and so you have to provide the linker the place to find sqrt's actual code. So you do that by the minus lm switch. So the task of a header file is to simply provide you usually with the declarations so that you can use it in your code, and the actual code is then added by the linker at the time of creating your executable. Okay.
Yes, sir. Thank you, sir.
Okay, so this is pretty straightforward actually. So this is printf. Printf is probably the most common library function that we have used. It simply puts some data on your screen. There are different things like %d stands for printing an integer, %lf stands for printing a float, %c is for printing a character, and there are many other ways in which printf can be used. We can probably have a different lecture altogether for just printf. The stdio.h is a header file that contains declarations for many uh, basic functions that you're going to require, things like printf and scanf, for example. Scanf is the function to take inputs. um, Main is essentially a place, a function from where your execution begins. So any program that is supposed to be executable must have a main, right? And the program starts executing from the first instruction within the main. Yeah, I think printf. So yeah, these are format specifiers, %d and %lf, and then for each format specifier in that particular order, you provide the values to be printed. Um, okay, this is, I think, running the first program. This is how you do that, GCC, and yeah, because you are not doing the -lm, you can see that this error is actually produced by the linker. In fact, and at this point, you can also try this. If you do GCC minus c quadratic equation for whatever it is dot c, it will go through, it will compile your code. Why? Because the compiler doesn't need to know the details of sqrt function. For it, just inclusion of math.h is fine, but the linker needs to know where the code is. So when you try to link it together, it will be a problem. But if you just want to compile it without making an executable out of it, you can give the gcc minus c switch. For that, you have to go through the last week. In the last week, I have given a showroom example in the code. So if you are interested in exploring the relationship between compiler and a linker, I'll also ask Avanish to put some more light on it. But that is the part where you have to understand the difference between a compiler and a linker. Okay, so we are done with this. Any questions here? We'll just go through probably one more. What is vector? So we have just 2.4. So we would have revised up to week 2. We have 3 minutes. Let me just try to do this. Okay, so now in the second version of this part, we basically said that now we are going to take some inputs. The quadratic equation that we were trying to solve now has become generic, and this is how we used scanf. By the way, scanf is very similar to printf. The only difference here is that scanf expects that the user types the input in exactly the same fashion as it is written here. So basically, it expects that the user types a equal to 1, comma, space, b equal to something, 3, comma, space, c equal to something. Okay, and then press enter. So basically the user is supposed to type it in exactly this format in order to make scanf parse the inputs out of it. So this is the basic use of scanf function. um, it is just like printf gives you a well formatted input, a well formatted output. Scanf expects a well formatted input. Okay, and if the input is not well formatted, you're going to see all kinds of things. And by the way, there is another difference here. You are going to use the address of these variables using %a, %b, %c. So now you know that this is basically call by reference. Okay, and whereas in printf it is just call by value. Okay, so /n is used for adding a new line to your output. There are many escape characters like this. /n is probably the most commonly used. And this parenthesis thing is essentially the whole idea of precedence. You need to know what precedence a particular operator has. Usually you have to only remember things like this, that slash and asterisk are at the same level, but they are higher than plus and minus. Okay, so if you want this thing to be calculated first, you just put them into parentheses. So for any case wherever you are in doubt, just use parenthesis, and parenthesis will work. Okay, and it is not really BODMAS. It is basically left to right in most cases, except a few that you guys already know. So the compiler evaluates everything from left to right, and of course the operator which has higher precedence, it is evaluated first. uh, yeah, this I think we have already seen. Okay, we are done. So I think up to week 2 we have made a revision, and it's 11 a.m. Any questions? Oof, okay, that was hectic. So we have revised up to week 2, guys, and we'll continue this tomorrow. Any queries? I need some water. Okay, guys, we'll meet on Tuesday now. Monday we won't be meeting. I mean, we'll be meeting over the weekend if you guys are coming to the lecture by Avnish, and otherwise we'll all meet on Tuesday. Okay. Okay. Bye, guys.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Thank you.